Hi everyone, for today's lesson we are going to learn how to simplify square roots and rationalize denominators. Our learning targets for today is for you to be able to say, I can simplify expressions containing a square root, including rationalizing the denominator. That might be a phrase that you remember back in geometry or in Algebra 1. And I can solve quadratic equations using square roots. This second part is going to be something that we are going to be focusing on in day 13 primarily. So let's go ahead and think back to when we were learning about perfect squares and square roots. Let's go ahead and list our perfect squares. Originally it says 1 to 12, but I'm changing it to 1 to 20 because truly you will need to know all of these values in this class, because not only are we using it for this lesson, but we will be using it for future lessons once we get into later units. So we have 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, 225, 256, 289, 324, 361, and 400. These are all of your perfect squares from 1 to 20. Others that you might see would be 625, comes up quite a bit, and that is 25 squared. So I want you to be aware that these are the numbers that I need you to know and study and memorize, because we will be working with these numbers quite a bit in this school year. So I'm zooming it out so you have an opportunity to write everything down. So recall that a number, r, is considered a square root of another number. We'll call it s, if r squared is equal to s. So like 5 is the square root of 25. That's because 5 squared equals 25. In order for us to solve this type of equation or to talk about square roots, we would say like the square root of s would be considered a radical. That whole expression is considered a radical, where the square root symbol is called a radical symbol. The s that is beneath the radical sign is called the radicand of the expression. So s that is beneath the square root is called the radicand. And it's called a square root symbol. It can be also referred to as other types of symbols like a cube root or fourth root or fifth root once we get into later topics. But for right now, we're just going to be working with square roots. This radicand is not just a number or a letter that's underneath the square root, it's the expression that is under the square root symbol. Now, also recall that a square root expression is fully simplified if the following conditions are true. The first condition being that there are no perfect square factors other than the number 1 in the radicand. And I say the number 1 because everything's divisible by the number 1. You want to make sure that there doesn't exist a factor of a 4, a 9, a 16, etc. underneath that square root symbol. Next, you want no radicals to appear in the denominator of the fraction. If you do have radicals appearing in the denominator of the fraction, you will have to do a process called rationalizing the denominator. And we will talk about that in just a moment. So some properties that I need you to be aware of is the product property. The product property of square roots looks like this. If you have a square root of two pieces that are being multiplied by each other, you are allowed to separate this expression into the square root of A times the square root of B. This is only true if you have multiplication underneath the radical. If you have something else like addition or subtraction, you are not allowed to use this product property. And that it goes in reverse as well. If you notice that two radicals are being multiplied by each other, you can put them together underneath one radical. So this is a very commutative property. Let's go ahead and look at a quick example of this. So we have the square root of 98. What we want to look for is we want to look for a perfect square factor that can go into 98. More specifically, you want to look for the largest perfect square factor that can go into this number. So whenever I'm thinking of 98, I'm going to see if I can make 4 work, 9 work, 16, 25. Let's go 98. I don't know much about 98, but I do know maybe it's divisible by 2. Look at that, 2 and 49. So I'm going to rewrite this as the square root of 49 times 2. And I like to put my perfect square first because of the way that my answer is going to turn out. And so we can split this apart into the square root of 49 times the square root of 2. And so that is my largest perfect square factor times my non-perfect square factor. So 2 doesn't have any other perfect squares in it, so that's how I separate it. And now I'm going to take the square root of 49, and that's going to equal 7. And I'm going to leave the square root of 2. So my answer is going to be the square root of a whole number times the square root of my non-perfect square factor. And that is the structure that your answer will be in. So let's go ahead and look at letter A. We have 48. And whenever I think of 48, I know that there exists a lot of numbers that can go into 48. I know that 4 can go into it, 4 times 12. But what about something else? In reality, 16 is the biggest number that can go into 48. So you always want to work with the biggest number. So let's go with 16. This is the square root of 16 times 3. And I know that the square root of 16, that is 4. So my answer is going to be 4 times the square root of 3. Let's say that you missed that. Let's say you saw 4 and you made this the square root of 4 times 12. That's perfectly fine. You'd end up with 2 square roots of 12, but because 12 has a perfect square factor in it, you have to keep going. Because your job is to fully simplify these radicals so that they have no more perfect square factors underneath them. So to keep going, this is going to be 2 times the square root of, I know that 4 can go into 12, so that is 4 times 3. So I'll have 2 still on the outside, but the square root of 4 is 2 times the square root of 3. And our answer is going to be, once again, 4 times the square root of 3. So you'll end up with 4 times the square root of 3 no matter what. Same thing goes with the number 80. Whenever I think of 80, I always think of 8 and 10, but 8's not a perfect square factor. I also know that 4 can go into it. But in reality, 16 is the biggest perfect square factor. So I'm going to take the square root of 16 times 5, and that answer is going to be 4 times the square root of 5, because the square root of 16 is 4. 24. I know that 4 is the biggest perfect square that can go into 24. So that's 4 times 6. And the square root of 4 is 2. So this is 2 square roots of 6. Whenever we are multiplying radicals, we always multiply the outside times the outside and the inside times the inside. That's how you would multiply. Outside times outside. So that's going to be 2 times 3 to give us 6. And inside times inside, that is 10 times 15, which is 150. So looking at 150 and our perfect square factors list, I'm leaning towards 25. as being my perfect square factor that can go into 150. And when I go 150 divided by 25, I end up with 6. So this is going to be 6 times the square root of 25 times 6. The square root of 25 is 5, so this 6 on the outside stays on the outside, but the square root of 25 is 5. The square root of 6 stays inside because it doesn't have a perfect square factor. So therefore, my answer is 30 times the square root of 6. Please go ahead and try the solo problems on your own and be ready to discuss them when I see you in class next. Here we go. Next page. So now we're going to talk about dividing square roots. And the quotient property for square roots is that if you see the square root of a fraction, you are allowed to take the square root of the numerator and divide it by the square root of the denominator. Same thing is true if you had a square root over a square root. You're allowed to put those values all together underneath one fraction. Always look for a relationship between the numbers and always look for perfect square factors as well. So looking at this example, we have the square root of 2 over 25. 2 and 25 are not related to each other. So I'm going to take the square root of 2 and divide it by the square root of 25. I now end up with the square root of 2 on top. There's nothing I can do about that. And the square root of 25 is 5. That is simply my answer. So let's go ahead and look at example number 2. If there exists a relationship, you would simplify those numbers, but in this case, we're just going to take the square root of the numerator and divide it by the square root of the denominator. The square root of 100 is 10, and the square root of 169 is 13, so my answer is 10 over 13. For letter B, I'm going to take the square root of 11 and divide it by the square root of 144. This is equal to the square root of 11 divided by the number 12. And that is simply our answer. Please go ahead and do C and D on your own. What was really nice about these examples is that we were not left with a root or a radical in our denominator. So because we didn't have to deal with that, we didn't have to do a process called rationalizing the denominator. Now, what happens if you still have a radical in that denominator? What are you going to do? Well, we have to do a process called rationalizing. So the process of eliminating a radical from an expression's denominator, so from the denominator, is called rationalizing the denominator. So this is called a root in your bottom. Nobody wants to have a root in their denominator. Nobody wants to have a root in their bottom. So there exists ways that we can make sure that that is eliminated. So let's say that your denominator is just a square root, like the square root of b is in your denominator. How do you get rid of that square root? Well, you would multiply both the numerator and the denominator by the square root of b. So why this works? Well, it works because if you have a denominator of square root of b and you were to multiply the square root of b times the square root of b, this would equal the square root of b times b, which is b squared. And what's really cool is that a square eliminates a square root, leaving you with just the letter b. The radical completely goes away, and you were simply left with the number itself. You might see a plus a square root. If you see a plus a square root, you will need to multiply this both the numerator and the denominator by a minus the square root of b. This expression of a minus the square root of b, and what we'll have down here is a plus the square root of b. These expressions are what we call conjugates. They are conjugates of each other. And that's because their product, when you multiply them together, will always equal a rational number. And a rational number simply means it's a number that we can reason out. It's a number that that will be nice to work with. It's a rational number. It might be positive, might be negative. Here's why this works. if I were to multiply my denominator of a plus b, a plus the square root of b, and I were to multiply it by a minus the square root of b, look at what the structure is. A and a, square root of b, a plus and a minus. This is dots. This is a difference of two squares when you FOIL it out. Let's check out the FOIL. I'm just going to go right into this box because as you guys can see, we're working with the same exact values. A plus square root of b, a plus square root of b, a minus square root of b, a minus square root of b. It's always opposite signs, but the values remain the same. I'm going to FOIL. A times a, that's going to give me a squared. A times minus b is minus a times the square root of b. The square root of b times a is plus a times the square root of b. And the square root of b times the square root of b is minus the square root of b squared. Combining like terms, I have a squared, negative a times the square root of b plus a times the square root of b. They cancel away. And I have minus the square and the square root eliminate, leaving me with the letter b. So it's going to end up being a rational number. A squared minus b is going to be a number that I will be able to simplify. All right, let's go ahead and look at example number 3 and apply this idea. So the first thing that we're going to do is, looking at this problem, just like we did before, I am going to split this apart into the square root of 2 over the square root of 15. But unfortunately for this problem, I can't do anything. The square root of 15, that's not a perfect square. I'm stuck. And whenever you're stuck, what you need to do is rationalize the denominator by multiplying both the numerator and the denominator by the radical that is in the denominator. And that, is the square root of 15. So I'm going to multiply 2 times 15, and that is going to equal 30. Divided by, this is the square root of 15 times 15, which is 15 squared. So this is the square root of 30 divided by, the square eliminates the square root, leaving you with just the number 15. There does exist some shortcuts with this. As you are working, you'll discover those shortcuts. But there's something I need to warn. The square root of 30 is not the same number as regular 30. The square, and you cannot eliminate or divide this out to become the number 2 or the square root of 2. That is a misconception that kids have. So what I'm going to do is I'm going to put in the square root of 30, and I'm going to divide it by 15, and I end up with this number. A lot of kids think that this answer is 2. This number is not 2. A lot of kids think that this is the square root of 2. Well, the square root of 2 is 1.41. These numbers are not equivalent to each other. So there is nothing further for you to do. We leave our answer just like this. The square root of 30 over the over regular 15. Square roots are allowed to be in numerators. They are not allowed to be in denominators. So that is the long story short when it comes to these types of problems. For letter B, we have 4 over 5 minus 3 times the square root of 2. And what we need to do is we need to eliminate that root in the denominator. And because it has subtraction, I am going to multiply both the numerator and the denominator by 5 plus 3 times the square root of 2. Now, because it has a plus and a minus, you need to have parentheses, because what we are going to do is we're going to use the distributive property and FOIL. So I'm going to distribute 4 times 5, and when I do that, I end up with 20. And then I'm going to multiply 4 times 3 to get plus 12 times the square root of 2. Down below, I would recommend that you use dots. It's going to be your first term times your first term, which is 25, minus your last term times your last term, which is 3 times the square root of 2 squared. So it's your first term squared minus your last term squared. This is a dots. If that is too confusing, FOIL it out. You'll end up seeing that it becomes a dots. we were left with up here a squared minus, and that ended up being my last term squared that I was able to eventually simplify. So how do you simplify 3 times the square root of 2 squared? Well, because the operation between them is multiplication, I can distribute the square to each piece. So this is going to become 20 plus 12 times the square root of 2 all over 25 minus 3 squared is 9, and the square eliminates the square root, leaving you with 9 times 2. According to the order of operations, we have 20 plus 12 times the square root of 2 all over 25 minus 9 times 2, which is 18. So this is 20 plus 12 times the square root of 2 all over, and this becomes, I want to say 7. And if we were to write this as 2 pieces, this would be equal to 20 over 7 plus 12 times the square root of 2 over 7. Both ways I will accept, just putting that out there, but eventually separating these pieces is going to be something that we will be working with in our in a couple of lessons. So I just wanted to put that out there. Our last example for this lesson is the same exact idea. This time around, we have a plus in our denominator, and what we need to do in order to eliminate it is to multiply both the numerator and the denominator by 2 minus the square root of 10. Anytime that you see a plus and or minus, you need to put parentheses because that means that you are going to be foiling or using an expanded version of the distributive property. In my numerator, I'm going to FOIL, and I'm going to multiply 3 times 2 to get 6. 3 times minus 10 to get minus 3 square roots of 10. 2 times the square root of 7 to get plus 2 square roots of 7. And the square root of 7 times negative square root of 10 is minus the square root of 70. This is all over. I need you to recognize that this is going to be a dots. And a dots means that you're going to square your first term. 2 squared is 4. Minus the square of your second term. So that is the square root of 10 squared. So this is 6 minus, and if we could combine our radicals together, we would. But because the square root of 10 and the square root of 7 are different radicals, we can't combine them. It's like variables. If this is like a 3x and this is a 2y, you can't combine them. 70 does not have any perfect square factors, like it's not divisible by 4 or 9 or 16 or 25 or 36 or 49, so we cannot do anything with the square root of 70. So we just leave our numerator the way that it is, and we have some cleaning up to do in our denominator. So this is all over. The square eliminates the square root, leaving us with 4 minus 10. So my final answer is going to be 6 minus 3 times the square root of 10 plus 2 times the square root of 7 minus the square root of 70 all over negative 6. Now, typically we don't leave the denominator as a negative. So what that means is we pull that negative up top and we change all of the signs to their opposite signs up top. So our actual answer is negative 6 plus 3 times the square root of 10 minus 2 times the square root of 7 plus the square root of 70 all over positive 6. Now, if all of these numbers had like a number that was divisible by 6, we could simplify even further. But unfortunately, we can't. So therefore, we leave this value or this expression as simply our answer. Please feel free to go ahead and finish the team and the pair on your own and be ready to discuss